Alrighty, so now that we've seen what a linear transformation is, let's understand why we care about it so much in the context of matrix theory. Well, I can succinctly say why we care in a single theorem. A transformation T from Rn to Rm is linear if and only if there exists a matrix A, which is an M by N matrix, such that T of X is defined as A times X. So not only are all transformations induced from a matrix linear, they're only, like, linear transformations are those that are only induced by matrix multiplication on the left. And so this is why linear transformations are not only important, but also very nice to work with, right? Because, well, if you know how to work with matrices, well, then you're implicitly working with transforming one space into another. The first question that you probably ask is, well, great, but how would I know A? How would I be able to find the matrix A, right? And so that's a good question, and we'll address that here. So here's another theorem. Let's let T from Rn to Rm, if this is linear, then the matrix A such that T of X equals AX is given by, so you take T of the basis vector E1, like the standard basis vector E1 for Rn, right? For the first column. For the second column, you take T of E2, et cetera, column vector T of En. And so if you can compute the transformation, or how the transformation transforms the standard basis vectors for Rn, then you know the matrix for, the matrix A that represents or kind of induces this transformation. So I mean, for a very quick example here, let's look at T from R3 to R2, defined by T of 1, 0, 0 is equal to 1, 2, T of 0, 1, 0 is equal to 9, negative 3, and then T of 0, 0, 1 is equal to 1, 1, right? Well, we have the transformation defined on the all elements of the standard basis for R3, right? Because remember, E1 is 1, 0, 0. Well, here, that's E1, this is E2, and this is E3. So pretty quickly, you can understand that A is the matrix 1, 2, 9, negative 3, 1, 1, right? Because you look at the image of all the basis vectors under T, and then the juxtaposition of those those resulting vectors, the juxtaposition of those column vectors into a matrix gives you the transformation. Well, that's fine if we're given this explicitly, right? I mean, if you come across a transformation in the wild someday, it most likely won't give you how it acts just on the basis vectors. So how could we find the matrix A without knowing how it acts on basis vectors? Well, we have the following method. Let's suppose T from Rn to Rm is defined on not necessarily the standard basis of Rn, but just some collection of vectors in Rn. Let's say A1 through AN. But we need the restriction that this is defined on these vectors such that the matrix composed of these column vectors here, A1 through AN, the inverse exists. Okay, and so these are column vectors. When I draw these little bars up and down, I'm trying to it's not necessarily a well-known notation, but just showing that they're column vectors, right? So we have a collection of vectors. We know how T behaves on this collection of vectors, and we also know that the matrix composed of the column vectors exists. And well, since we know how T is defined on A1 through AN, then T of AI is going to equal some BI, right? So we implicitly know this as well. Then the matrix C such that T of X equals CX is given by, well, let's say these BIs, right? So B1 through Bn, these will also be column vectors, right? And then times A1 through AN here. So sorry, we have a map from Rn to Rm. That means B should be, this should be M, my apologies, right? And then we take the inverse, and this is our matrix that represents this transformation. And so this is the general method, right? When you don't know how it acts on basis vectors, you just know how it acts on some collection of vectors, right? Well, you compute the inverse, and then you take, right? So if we were to call A, if this was to be the matrix A1 composed of the column vectors A1 through AN, and then B was the matrix B1 through BM, well, then C is always just going to be BA inverse, right? So we could see a quick example here. Let's let T be a map from R3 to R3 such that, and we know how it acts on, let's say 131, which is 0, 1, 1. We know how it acts on 0, 1, 1, which is 2, 1, 3. Sorry, equals 2, 1, 3. And then we also know how it acts on 1, 1, 0, which is 0, 0, 1, right? Then the question is, what is the matrix C such that T equal, well, T of X equals CX, right? Basically what I'm asking is, or what this question is asking is, what's the matrix that induces or understands or represents this transformation T, right? Well, first we need to construct this matrix A that's composed of where the column vectors are A1 through AN. So what would that be, right? Well, the A1 through AN are the vectors that we know how it acts on, right? And it's acting, this transformation, we know how it acts or how it is applied to 131, 0, 1, 1, and 1, 1, 0. And so for that reason, we have A is the 3 by 3 matrix, 1, 3, 1, 0, 1, 1, and then 1, 1, 0, right? And then B is the matrix of resultant vectors, right? Because we're saying the image of these AIs is these BIs here, right? So that means for B, well, what's the result from 1, 3, 1? That's 0, 1, 1. The result from 0, 1, 1, or like after you apply, right? T of 0, 1, 1 is 2, 1, 3. And then after you apply 1, 1, 0, you get 0, 0, 1. And then so the matrix representing this transformation is BA inverse, which is, you know, calculate the inverse, take the product. We're pretty good at that by now, hopefully. And the result would be 2, 0, 4, negative 2, 0, negative 3, and 4, 1, 6. Okay. And then here's a problem for you guys to do. Again, I can't assign it for points, but I'm assigning it, right? So I want you to verify I'll say star, and star is these 3 properties, right? I want you to verify that when you apply this matrix, right? Like for the first one, you would need to show that 2, 0, 4, negative 2, 0, negative 3, 4, 1, 6 times. And what are we doing? We're applying the vector 1, 3, 1. I want you to verify that this, in the first case, you do indeed get 0, 1, 1. And I want you to do that for the second and third vectors here as well. Okay, so next I want to, well, let me describe a few properties here. I want to give a small list of properties, and then I'm going to, I think it's more beneficial to break here after these properties, and then make a very short video about, like, hopefully not even 10 minutes, about the composition and inverse of a transform. So we have some important properties that are worth writing down here. I'd like you to see if you can prove these as well. So here's an exercise. Prove these. Okay, the first property is that, well, so let's say first T from Rn to Rm is a linear transformation. Okay, so these are properties of linear transformations. The first property is that T of the 0 vector is always 0. The second property is that T of negative x is negative T of x. And then the last property is that the linearity property doesn't just hold for 2 vectors. It holds for an arbitrarily large finite number of vectors. And what that means is like T of A1, if A1 through AK are constants here, like T of A1 x1 plus blah, 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 through AK xk, this is equal to A1 times T of x1 plus, and I'll write a second one out over here so we get the idea, A2 T of x2 plus blah, 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 plus AK T of x. Okay, so I want you to see if you can prove these properties. And I'm going to break here to make 2 smaller videos. And in the next video, we'll talk about the composition and inverse of a linear transformation.